All right, now let's look at number 5 about Stokes' theorem. This is a pretty complicated, tough concept. But here is an explanation. This thing right here can fit into Stokes' theorem this way. This will equal the integral over some region C of some vector field F dot dr for that region, being like a radius of a region where that field is located. Alright, that's kind of just very vague. But let me see if I can, once we can get the components of this little theorem, it won't be so bad. So F in this case is basically all these things. But think of them as a vector. So it would be like F would be, let me write it like this, 2y cosine z for the x component, e to the x sine z for the y component, and x e to the y for the z component. It's like the ijk, okay? Like the first element, second element, third element. A lot of times I like writing them in this column form. Doesn't matter how you write it, really. Okay. R think of R. We're going to get R from this. This is what's going to be so confusing. R comes from x squared plus y squared plus z squared equals 9, where z is greater than 0. Which is kind of, it's basically this hemisphere. Okay. It's this hemisphere. This dome right here is what that's a graph of. If z was not greater than or equal to 0, it would be a sphere. It would be a sphere with radius 3. But because z is greater than or equal to 0, it's a hemisphere, a dome on top, the top half only. Alright, now, the region is actually just this circle on the xy plane that dome intersects, where that dome intersects the xy plane. So that's just going to be where z is 0. This term can go away. It's just going to be x squared plus y squared equals 9. Okay? Now we're going to do what's called parameterize this thing into polar coordinates. Alright, so for polar coordinates, if you want to do an x coordinate, the x becomes r cosine theta. And that makes a lot of sense if you can think about it for trig, right? So wherever we are right here, this is r, this is theta. Okay, the x component is r cosine theta, and that's just trig. That's just trig working itself out with that right triangle. And the y component is r sine theta. So y is r sine theta. Okay, so if we're going to parameterize r, so in other words, I want to make r be a function of theta, then it's going to be, the x component is going to be 3 cosine theta. Where did I get the 3? The 3 is the radius of this circle for this region C here. The y component is 3 sine theta, and the z component is just going to be 0, because we're just in the xy plane for that region. Alright, so but I need dr. Dr or r prime of theta, in other words, is equal to the derivative of r of theta, which is going to be negative 3 sine theta, 3 cosine theta, and 0, which is just taking the derivative of each of these components. All right, keep in mind, like, this is the x component, this is the y component, this is the z component. So we're now almost, we've taken some good steps. We've got dr. We need to do some work on f to get it compatible with dr. We're going to express f as a function of r, and r happens to be a function of theta. So we're going to find f of r of theta by using 3 cosine x wherever there's an x, 3 sine theta wherever there's a y, and 0 wherever there's a z. So it's going to be 2 times 3 sine theta times cosine of z, which is 0. That is the x component now of f. The y component will be e to the x, x being 3 cosine theta, and then sine of z, z being 0. And then the z component is going to be x, x being 3 cosine theta, e to the y, that's going to be e to the 3 sine theta. Okay, let me simplify that. There's some simplifications we can make. What is cosine of 0? Cosine of 0 is 1. So this becomes 6 sine theta. What about sine of 0? Sine of 0 is 0. So that whole thing becomes 0. And then this one won't really simplify, so it's just think this is what it is: 3 cosine theta, e to the 3 sine theta. All right, if you're lost on this problem, don't worry too much. I understand. You may want to go back and look at it a couple times, or if you just can't do this kind of problem, you know, it's not the end of the world. All right. So now I've got f in a way that I can dot product that thing with r. All right, let me work on that. So it's now the integral of f dot dr is equal to the integral of this f of r of theta, 6 sine theta, 0, 3 cosine theta, e to the 3 sine theta, dot negative 3 sine theta, 3 cosine theta, 0. Remember, a dot product is just multiplying the x with the x, add that with the y times the y, add that with the z times the z. That's how you do a dot product. Which is going to equal the integral of negative 18 sine squared theta plus 0 times 3, that's just 0, plus this thing times 0, which is again 0. And now it's just going to be d theta. Alright, so let me just simplify that now just a little bit. Let me clean it up. D theta. Alright, Alright, from here it's going to get even more strange. I'm just moving this up here to have more room to work. The integral of sine squared is a lot more complicated than it looks. U substitution doesn't work. What can work is this identity, this trig identity, where sine squared theta is equal to 1/2 minus 1/2 cosine of 2 theta. So I'm going to substitute that in. So now this equals, I'm going to move the 18 outside, integral of 1/2 minus 1/2 cosine 2 theta d theta. Alright, I'm also going to factor out the 1/2. So that's going to become, so if I factor out a 1/2, this becomes -9 outside. Then it becomes 1 minus cosine 2 theta d theta. Okay, so I'm just going to separate it, -9, the integral of 1 d theta minus the integral of cosine 2 theta d theta. -9, the integral of 1 d theta is just going to be theta. This one's going to take even more integration tricks, like U substitution. So if I let U equal 2 theta, then du d theta equals 2. So du over 2 equals d theta. And so this becomes the integral of cosine of u du over 2. So it's 1/2 integral of cosine of u du, which is 1/2. The integral of cosine is sine, so sine of u, and u being 2 theta. So sine of 2 theta. That's that integral. So minus 1/2 sine of 2 theta. I forgot I need to multiply that -9 by that also, so minus 9/2 sine of 2 theta. Alright, so then this is integrated now, and I have to go, I forgot to put, at some point I need some limits of integration. What should they be? Let's go back and look and see what they should be. Remember this little picture here where you had this dome, but where it intersected the XY plane is the region of C, the boundary region. Well, since we're in polar coordinates, then we are going around all the way around. What is theta when you go all the way around? Theta is 0 to what? 0 to 2 pi. So that we're integrating from 0 to 2 pi. That's what we're integrating on the variable theta. Alright, now that is, I don't think I'm going to factor out that 9 again. I should have just left it factored out. Theta minus 1/2 sine 2 theta. This theta goes from 0 to 2 pi. So that's going to equal -9, 2 pi minus 1/2 sine of 2 times 2 pi, so that's sine of pi, minus 0 minus 1/2 sine of 2 times 0, which is 0. Well, what is sine of 0? Sine of 0 is 0, so that's just 0. That whole thing is 0. what is sine of pi? Sine of pi is also 0. So that's just 2 pi then. So it's negative 9 times 2 pi, which is negative 18 pi as the final answer. Now that was just some crazy work, wasn't it? It was. They don't call it Calc 3 for nothing. Maybe the problem on your assessment might be simpler than that. But hopefully that gives you at least some idea of what's going on and some chance at that problem. Alright, number 6. We're just finding a partial derivative here. df dx. We're taking the derivative of this with respect to x. So this is y over x. So it's like a constant over x. So if we had any constant over x, 3 over x. By the way, the derivative of 1 over x is ln x. So the derivative of 3 over x is 3 ln x. So the derivative of y over x with respect to x is y ln x. The derivative of cosine squared of y with respect to x, that just means that's just a constant. So the derivative of a constant with respect to x is just 0. So this is the only answer. Alright, here is number 7, doing a triple integral. We will do the inside integral first. So we're just doing the integral from 0 to 2 of rho squared sine phi d rho. And yes, this is the Greek letter rho, and it is my favorite of the Greek letters. So we're just integrating with respect to rho, which means sine of theta is just a constant. So the antiderivative of theta squared is theta cubed. The constant just remains there, so it's going to be the integral of rho squared is rho cubed over 3. And then the sine theta is just still there. And we're integrating that from 0 to 2. And we're just substituting the 2 and the 0 in for rho, not for theta, because rho is the variable of integration here. So it's going to be, I'm just going to leave the sine theta out here for a second. So it's just going to be 2 cubed. I'm also going to leave the 3 out here for a second. 2 cubed minus 0 cubed, which is going to be, that whole thing is just 8. So this is going to be 8/3 sine theta. And now I'm integrating that was it a theta? No, it wasn't a theta, it was a phi. I'm sorry. That whole theta thing is supposed to just be a phi. Not a theta. And that's d phi, d theta now. So now I'm doing this inside. The next layer from the inside of the integral. So I'm just doing that one. So the integral from 0 to pi of 8/3 sine phi d phi. That's all I'm doing in this step. So the integral of sine of phi is negative cosine phi. So this is going to be 8/3. I'll say negative 8/3 cosine phi. Let's put my negative in front there. And we're integrating that from 0 to pi, which is going to be, I'm just leaving my 8/3 out here for a minute. And I'm just going to do cosine pi minus cosine 0. Cosine of pi is -1. Cosine of 0 is 1. So -1 minus 1 is, that whole thing is -2. So then this whole thing is -16/3. So now I'm just down to the integral from 0 to pi of -16/3. d theta, which is going to be just negative 16/3 theta from 0 to pi. So it's negative 16/3 and then pi minus 0. So that's just negative 16/3 pi. And that's the answer. Alright, more triple integrals on number 8. Do my inside integral first. The integral from 0 to z over 4 of r to the 4th dr. That's just going to be r to the 5th, 1/5 r to the 5th, evaluated from 0 to z over 4. And I could just leave my 1/5 out. So that's just going to be 1/5 z fourths to the 5th minus 0 to the 5th, which is going to be, that's going to be 1/5 times z to the 5th over, good gracious, what is 4 to the 5th? That's a big number. Let's see, 16 times 16. Is that 324? Am I remembering that right? No, I'm not. Is it 316? 8, 9. $256. I sure didn't remember that correctly. Oh, and then I got to multiply that times another 4 because it's 4 to the 5th. 4 carry 2, 20, 22, carry 2, 9, 10, 10, 24, 10, 24. Yuck. And then that would be 240. 5,120. Yeah. I don't like this so far, but got to keep going. So now we're going to do this integral. So it's the integral from 0 to 4 of z to the 5th over 5120 dz. Okay. Alright. That's going to be z to the 6th over 6. And I got to multiply 6 times 5120. Let me get my calculator. That's 30,720 from 0 to 4. To the 6th minus 0 to the 6th. Okay, so 4 to the 6th. I bet there's some canceling that could be done here. Let's see what happens. That's 4,096. Over 30,720. Let me see if there's some reduction. I think this reduces to 132 over 990 if I have done it correctly. And so then that goes into there to finally do the last outer integral, the integral from 0 to 2 pi of 132 over 990 d theta, which is just going to be 132 over 990 theta. As theta goes from 0 to 2 pi. I could have just done that, left the other part outside, which is just going to be 2 pi. So yeah, that's 132 over 990 times 2 pi. Now, probably the 2 can cancel there. What's half of 990? 450 plus 45. That's 495. So it looks like the answer is 132 over 495 pi. Right, number 9 is a divergence theorem problem, and it is similar to this Stokes theorem and Green's theorem problems. Alright, so what we're doing is basically we're going to do this triple integral right here. This is the divergence theorem kind of stated in a vague mathy nerd way. Okay. Now f, what is f? F is it's kind of this function right here. It's x to the 4th I, or let's just do it this way. It is x to the 4th. It is negative 4x cubed y, and it is 7xz. If we want to write it in that form for a vector. And so basically this is m, n, and p, or we can do it like this. This is m, n, and p. And so if I'm trying to do this part right here, that's kind of the gradient symbol, and it means you're taking partial derivatives with respect to each variable. So just look at this to tell what to do. This right here tells us what to do. To do the gradient dot f, we're just doing the partial derivative of m with respect to x plus the partial derivative of n with respect to y plus the partial derivative of p with respect to z. So let's do that. Alright, partial derivative of m with respect to x is going to be the derivative of that with respect to x, which is 4x cubed. Partial derivative of n with respect to y is going to be the derivative of that with respect to y, which is just going to be negative 4x cubed. And the partial derivative of p with respect to z is just going to be 7x. Okay, so now we have the gradient dot f. So let me just write this explicitly and simplify it. Gradient dot f equals 4x cubed minus 4x cubed plus 7x, which is just 7x. So now we're doing the triple integral of 7x dv. But we are integrating that over a spherical surface. And to do that with just regular old XYZ coordinates, in other words, rectangular coordinates, that's going to be really difficult. Spherical coordinates actually can make this simpler. Here's one thing you can use for spherical coordinates. Anytime you've got x, that can be redone as rho sine phi cosine theta, which makes a lot of sense. If you can visualize this, if we're doing, x, y, z, we got to go in the x direction, then the y direction, then the z direction. Why is it doing that? Then the z direction to end up with some point in space. But if you're doing spherical coordinates, rho is like a radius, so you're going some radius outward. Then you're rotating some angle phi. Then you're rotating up some angle theta. And you end up in the same spot. So that's how these things are related trigonometrically with this relationship, this expression right here. The x coordinate is just phi sine phi is just rho sine phi cosine theta, and some trig, showing some trig up here would show you that. I'm not going to do that at this point. Alright, dv also has a relationship. dv is equal to rho squared sine phi d rho d phi d theta. Now let me check myself and make sure I remembered that correctly. So now this is going to be the triple integral of 7 times x, where x is now replaced with rho sine phi cosine theta, dv, where dv is replaced with rho squared sine phi d rho d phi d theta. All right, that's a pretty grand expression right there. I think we can simplify it a little bit. This is equal to the triple integral of 7 rho cubed, because that rho and that rho squared, and then sine squared phi, because that sine phi and that sine phi, cosine theta d rho d phi d theta. Now we need some limits of integration. What should they be? All right, we're thinking now about this. We should now think about this sphere. Okay, I want you to think of this sphere. Okay, I'm not too good at drawing, but you can just imagine the sphere, okay? And this is the equation of that sphere. X squared plus y squared plus z squared equals 25. What do you reckon the radius is of that thing? The radius, or we may say rho now, is 5. So if we're integrating, the whole radius goes from the origin all the way out. We're integrating over the whole of the radius, so it goes all the way out to 5. So the limits of integration for rho will be 0 to 5. All right, if this is phi, phi starts with an angle of 0 and goes all the way around. So what does phi go? What are the limits of integration then for phi? It would be 0 to 2 pi. And then theta goes all the way, starts here, and goes all the way around here. So what are those limits for theta? Also 0 to 2 pi, as being a full revolution. All right, now let's try our best to, now that we've got the integral created, let's try our best to actually evaluate it and compute an answer. All right, so first we're going to do the inner integral with respect to rho. So that's going to be the integral from 0 to 5, 7 rho cubed sine squared phi cosine theta d rho. That's going to be 7 rho to the 4th over 4 sine squared phi cosine theta, evaluated from 0 to 5. Okay, so I'm just plugging in 5 for rho and then 0 for rho. Well, I plug in 0 for rho, I know that's going to be 0 anyway, so really just plugging in the 5 is all I need to do because of that. So that's going to be 7 times 5 to the 4th, which is the same thing as 25 squared. Is that 625? I think that's 625. I'm just going to leave it like that for now. Sine squared phi cosine theta Why is my pen writing so strangely? That is very strange right here on this part of my keyboard, or on my screen. Alright, and then that, hold that thought. So now I'm integrating that with the second part of this integral. This part. Okay, which is going to be the integral from 0 to 2 pi of that stuff, d phi. Alright, I'm just going to pull that constant outside of the integral. It's 4375 over 4 times the integral from 0 to 2 pi of sine squared phi cosine theta d phi. I'm trying to integrate this with respect to phi. The sine squared thing, we actually saw that earlier, and it's not easy. Where sine squared of well, let's just say phi to keep from getting confused. I can do a trig substitution where that's equal to 1/2 minus 1/2 cosine of 2 phi. Alright, so, and I'm even going to pull the 1/2 out, and it'll be 1 minus cosine of 2 phi. So, if I pull that 1/2 out, it'll be 4375 over 8. I'm even going to pull this cosine theta out, because that's treated as a constant also. And that's, in here it's 1 minus cosine of 2 phi, d phi. Alright, now, that's going to equal, the integral of 1 d phi is phi. The integral of negative cosine is going to be, let's see, the integral cosine is sine. So it's going to be negative sine of 2 phi over 2. And that's just, you can prove that out using u substitution as we did before. If you let u equal 2 phi, you're going to end up with this du over 2 equals d phi. So that d phi would get replaced by d over 2, and so then that's how the 2 came on the bottom there. That's how they got a 1/2. Now this is from 0 to 2 pi. So that's going to be it's going to be 2 pi minus 1/2 sine of 4 pi minus 0 minus 1/2 sine of 0. Sine of 0 is 0, so that whole thing is just 0. Sine of 4 pi, that's all the way back around to 0 again, so that's also 0. So that term becomes 0. So it's just 2 pi then. That's nice. That's a nice little simplification. So it's 4375 over 8 times 2 pi. And the 2 can cancel that and become 4. So it's just 4375 over 4 pi. That is the second integral. Now we got to go to the third integral. So finally, this last outer integral is going to be the integral from 0 to 2 pi of 4375 over 4 pi d theta. Yeah, I left something out. Let me go back and, because here's what I forgot. I forgot that cosine theta right there. That was supposed to be here this whole time. That was supposed to be here. And here. And therefore here. So pi cosine theta d theta. Alright, no problem there, I don't think. That's going to be 4375 over 4 pi. The integral of cosine, the outside derivative of cosine, is sine, so sine theta for 0 to 2 pi. And then that becomes 4375 over 4 pi sine of 2 pi minus sine of 0. And sine of 2 pi is 0, and sine of 0 is 0, and that's just 0 times that, which is just 0. And why is that the case? So what this is doing physically is it's telling us the amount of what's called flux. Flux that's coming out of the origin, out of this sphere in every single direction, every single infinitesimal number of directions in all three-dimensional directions out of that sphere. So, and if we think about that coming up this way is positive and going down that way is negative, then you can see that everything cancels out, positive and negative. So it does end up being a 0 net flux. So that should be right. And again, perhaps your question on the assessment may be slightly simpler than this, hopefully. Alright, number 10, we're finding the directional derivative. That means we're finding the derivative or the slope in a particular direction on this surface stuff. So the way that we will do that is we will first find kind of the unit vector for u. U is not a unit vector at the moment. We're going to turn it into a unit vector by first finding the length of it. The length of u, that's kind of what that symbol means, is the square root of 2 squared plus 9 squared plus negative 6 squared, which is the square root of 4 plus 81 plus 36, which is the square root of 40 plus 81. I think that's 121, which is 11, I think. So that means that the unit vector for u is a unit vector in the same direction as the original u, is going to be 2/11, 9/11, negative 6/11. The next thing we do is we find this. We've been seeing that symbol a lot. We're finding that, which means we're doing the partial derivatives with respect to every variable of f. We're finding df dx, df dy, and df dz. Df dx is going to be the derivative of this guy with respect to x. So the derivative of this term is just going to be y. The derivative of this term is 0. The derivative of this term is going to be z, so it's y plus z. The derivative of this with respect to y now is going to be x plus z plus 0 there. And the derivative with respect to z is going to be 0 plus y plus x. So those are my partial derivatives. Now I'm almost done. So now the derivative in the direction of u of f of x, y, z is equal to basically it's equal to this unit vector u dot this gradient vector of f. So in other words, it's equal to 2/11. That's the x coordinate, the x component, I should say, of that unit vector in the direction of u, times the df dx times the y plus z. I need some more room. Alright, plus the 9/11 times that's the y component of the unit vector, times the df dy, so times x plus z, minus 6/11 times, that's the z component of the unit vector, times the df dz, which is y plus x. And that's pretty much it, but I might be able to combine it some and maybe simplify a little bit. Let's just see. 2/11 y plus 2/11 z plus 9/11 x plus 9/11 z minus 6/11 y minus 6/11 x. Let's see if we can combine some like terms. That and that. 2/11 minus 6/11 y. That's going to be negative 4/11 y. And then 2/11 z plus 9/11 z. That's 1z, so plus z. And 9/11 x minus 6/11 x. That's going to be 3/11 x. So I just put it in the x, y, z order. You don't need to necessarily do that, but that is the derivative, the directional derivative in that of this function in this direction. It tells you how it changes, how this function changes with respect to x, y, and z in this particular direction of this vector. Alright, number 11, this is our last one. So again, doing the inner integral first. That's going to be the integral from 0 to square root y. I'm doing dx. I'm going to put 4e to the negative y out here because that's just constants as far as integral with respect to x is concerned. So that's just going to be 4e to the negative y of x squared over 2. Over 2 can come out here, and I can just make that 4 over 2 just be a 2. And that's going to be from 0 to the square root of y. So I'm plugging in the square root of y, and I'm plugging in 0. So that's going to be 2e to the negative y times the square root of y squared minus 0 squared, which is 2e to the negative y times y. So that cancels, and that's just 0. Okay. So then this becomes the integral, the outer integral now, from 1 to 2 of 2y, I'm going to write the y first, 2y e to the negative y dy. Now, this is going to get more difficult than we want it to be, but it's going to be. We're going to deal with it. All right, I'm going to move the 2 out here. And this looks innocent enough. I mean, it looks like, well, dog, shouldn't we just be able to integrate that? But U substitution won't work, and there's no, integral formula for this. We got to do integration by parts. Integration by parts, we have to remember what that is, and it is this. The integral of U dv is equal to U times V minus the integral of V du. So we got to turn it into that. And remember the, I think it was LATE or something like that, where it's like logs. I can't remember. Algebra. I think I'm missing a letter. Let me see if I can figure out what letter I'm missing. Yeah, LIATE. This is inverse trig. Algebra, trig, exponentials. That tells you what you should make your U, whichever one of these you come to first, reading it left to right. So the first one I come to is the algebra, which would be the Y. The Y is going to be the U, and the exponential is going to be the dV. Alright, so if U is Y, then du is 1. And if dV is e to the negative y, then v is the antiderivative of that, is negative e to the negative y. Alright, so now this is going to become 2 times u, which is y, times v, which is negative e to the negative y. Put the negative in front of the y, that's fine. Minus the integral of v, which is negative e to the negative y. So I'm just going to put that negative out there, which makes that a plus. E to the negative y du. And du is just 1. It's actually 1 dy. I forgot that. The chain rule, all that good stuff. The derivative of y is, with respect to y, is 1, but if I'm doing it with respect to u or respect to y, kind of like this, then it's going to be 1 with an extra dy right there. Just think of it like this. I'm doing a d on both sides. So du equals dy. So dy. Now, the integral of e to the negative y dy is negative e to the negative y. So now I've got 2 negative y e to the negative y minus e to the negative y. And I'm evaluating this from what? From 1 to 2. So now it's going to be 2, and it's going to be negative 2 e to the negative 2 minus e to the negative 2 minus negative 1 e to the negative 1 minus e to the negative 1. It's going to be 2. What would be the best way to write this? I'm not real sure. Let me just see what happens. Well, these are like terms, aren't they? So, two things minus 1, so negative 2 things minus 1 thing is negative 3 of those things, negative 3 e to the negative 2. And these are like terms. Negative 1 thing minus another thing is negative 2 of those things. So negative 2e to the negative 1. And that's going to be 2, negative 3e to the negative 2 plus 2e to the negative 1. And that's pretty much as simple as you can put it. I mean, I don't know that you can. Maybe we could. I mean, we might could do a few more things. Maybe you could leave it like this. But if I could try to do a couple more things. Let me see what happens. We could make this negative 6e to the negative 2 plus 4e to the negative 1. And I'm kind of debating now if I should try to go further. I paused it and did a little bit more work and got to that, but this is probably just as good an answer as that is. So anyway, that at least shows you how to go about evaluating that. And we could obviously type this in our calculator and get a decimal approximation of this answer, or we may need to just leave it like this for an exact answer. So again, that shows you what to do. Good luck on that assessment, and that's it.